Today we're going to talk about Kirchhoff's rules, and really we've been using them this whole time. It's just now we're going to apply them in the most difficult situations that you could encounter. So this Gustav Robert Kirchhoff uh, came up with two rules that can simplify circuit problems. So the first one being the junction rule, and we have been using this one when we talk about parallel circuits. So the junction rule helps us to calculate current through resistors that are in parallel. That's where we've seen it before. And any other point where a circuit breaks into a bunch of different branches. The other rule that we've already seen is called the loop rule. The loop rule just tells us that the voltage anywhere around any loop has to add up to 0. So we can use that one to calculate the voltage at any point. So let's say we have this diagram here. If you didn't copy it Friday, you may need to pause for a second and get this copied down. So before we can start to apply any of Kirchhoff's rules here, we're going to have to draw some arrows on the diagram. And all that's going to say is which way the current's going to flow through. So if we start at this battery, we know current likes to flow out of the positive, which means when we hit this 4 ohm resistor, R1, it has to flow to the right. Then we reach this junction. So remember, junction is where one splits into two or more, just where a bunch of different wires come together. So if we're going to the right, let's just say it would keep going to the right. So part of the current will keep going to the right, part of the current is going to go down through R2. Alright, so we're going to keep following our branch here around. Oh, whoa, that's weird. We're going the wrong way through a battery, but I mean, we're already kind of invested now. It's a little too late to switch. So we have current going the wrong way through a battery, which means it would come around through here and go across R3 to the left, and then we come back into another junction. So we had current coming down from above, so we can't go up. We had current coming to the left, so that means we're going to have to leave the junction this way, still going off to the left, and then we go back to our battery. Alright, so you can really draw the arrows in any direction you want to, as long as it makes sense, so you would be able to follow a path along and get back to where you started. I have two kind of different loops here, and if I follow the arrows around either one, I go right back to where I started. So what about this guy though, this one going the wrong way across the battery? It's kind of weird. But I mean, that was the whole thing that we just said. You don't have to have the arrows pointing in the right direction. When we apply Kirchhoff's rules, that'll take care of it. Everything will get flipped around the way it's supposed to be. Alright, so let's jump back into these rules. So the first rule, the junction rule. The junction rule says that any current you have going into a junction has to equal the current coming out. And that's just going back to the conservation of charge. So you have a certain amount of charge going in that has to be the same as the charge going out. So if a circuit separates into more than one branch, so like resistors in parallel, then the total current is just split up along the branches. So we've run into examples where we've had resistors in I think this right here, let me change this right here. I think that's supposed to say parallel. If we encounter three resistors in parallel, we know the sum of the current through all three resistors is equal to the current in the wire before it divides into three parallel branches. Yeah, that was a pretty bad typo there. Alright, so let's start applying this junction rule to this circuit that we've set up. So we're looking at just one section of that circuit that you had drawn before. So we're going to try to apply the junction rule to this diagram here. Alright, so if you look at what we have set up here, this is where our first battery would have been where we started at. And we came up here, and we're just going to arbitrarily assign that current I1. So we have current I1 flowing in through resistor 1, and then it hits the junction at B. So at B, we know we have to split apart current. The one that we said goes off to the right, we have I1 minus I2. So we take our total current, I1, and then just subtract whatever went off down the different paths. So we said I2 goes down through resistor 2. That means whatever's left over goes off to the right there. Alright, so really that's pretty much it for the junction rule. All we said is the current going into a junction equals the current going out. So if we look at B right here, the current going into it is I1. And it has to be the same as the current going out, so that is, what do we call it, I1 plus I2 I1 minus I2 plus I2. So if we do that little bit of math right there, I2 minus I2 is 0. So really all we have is I1 equals I1. So we know we've set it up appropriately. Everything that goes in is equal to what's coming out. The other rule, the loop rule, that's the one that addresses voltage drops. And that one tells us the sum of the voltage drops around any closed loop any closed loop is 0. So we've already been working with that one too. We've already said, we start out from the positive terminal of the battery with some voltage. When we get around to the negative end, it has to be 0. We've been working with that a long time. It's how we were able to solve for a lot of things. So whereas the junction rule was kind of a statement about conservation of charge, the loop rule is a statement of the conservation of energy. So every increase in potential energy, like from a battery or some power supply, has to be balanced by some decrease. So like a resistor has to be there to use up the energy. So voltage drop across all resistors in a closed loop is equal to the voltage of the battery in that loop. So whatever positive you have has to have a total matching negative. So if we were looking at one of our really simple circuits, then we know that whenever current crosses some resistor, then the voltage has to drop by I times R. That comes from Ohm's law. V equals IR. When the current crosses a battery, the voltage rises by V. So if we trace a loop around a really simple circuit, getting into these more complicated things, and we're tracing loops, we can do it in whatever direction we want. I like, when I do it, to follow the current arrows that I drew. Just helps me to keep track of what I'm doing and where my loops are going. But, I mean, really, you could do it whichever way you want. So, if we end up following our arrows and we cross a resistor against the direction of the arrows that we drew, then a resistor is going to act like something that increases potential. So we're kind of doing the opposite of what it's supposed to do. And if our loop crosses a battery in the wrong direction, that's also going to do the opposite. So if we enter the positive and go out the negative, we're dropping potential. So just real quick, voltage is going to drop by IR when the loop crosses a resistor the direction of the current arrows. Voltage is going to rise by IR when the loop crosses a resistor against the direction of the arrows. So if you go the right way, it drops. You go the wrong way, it raises. And then kind of opposite that, voltage is going to rise by V when you cross a battery from negative to positive, and it'll drop by V when you cross from positive to negative. So you go the right way, the battery does what it's supposed to do. You go the wrong way, the battery does the opposite. Alright, so let's use that loop rule to start working out what current is going through each of these three different resistors. Alright, when we set up our junction rule, we looked at this A, B, C, and E here. And we said that the current that goes past A through R1 is I1. The current that goes from B to E is I2. And the current from B to C is I1 minus I2. So we've set up two different variables for describing the current. So we are going to need two different equations to be able to solve for the variables. So luckily we have these two different loops here. You can kind of see this square section here and a square section here. So we have two loops. We can actually get those two equations that we need to be able to solve for our two different current variables. Alright, so we're going to look at the first loop, the one on the left-hand side. Now it's not fitting on one page. Alright, so remember the current between A and B is I1. The current between B and E is I2. And then E to D and D to A would also both be I1. So if we trace the loop clockwise from A, the current is going to cross over R1. Alright, so we trace from A, the current is going to drop over I1 because that's the way our arrows go. So we go with the arrows across the resistor, it causes some drop, I1 times R1. We keep following along. On our way from B to E, we cross over R2, going with the current, so the drop there is I2 times R2. Keep moving along from E to D, we don't encounter anything. And then from D back to A, we cross over a battery from negative to positive, so it's going to add 12 volts. Alright, so let's talk about this loop here in equation form. So we know everything has to add up to 0. So we crossed over R1 with current I1, R1. Then we crossed over resistor 2 with current I2. But remember that we cross these in the right direction, so they're actually causing a drop. Adobe. This looks better. Alright, so those resistors are causing a drop. And then the last thing we crossed over was the battery, which just added its own potential. And this one really is positive because we crossed it the right direction. So if we plug in a few of those values that we had, like our values for the resistor, then what we would wind up with is negative. I'm going to leave off the units for now so we can just focus on the math here. So R1 was 4 ohms. So we have negative 4I1. I'm just going to change it to minus right now. Minus R2 was 3, so minus 3I2. 3I2 plus the potential in that battery was 12. Alright, and we can clean it up a little bit more, make it look a little bit nicer. So 12 is equal to 4I1 plus 3I2. Alright, and that's the equation for our first loop. 12 is 4I1 plus 3I2. So we do the same thing for another loop. Alright, we can start anywhere we want as long as we make one complete loop around here. So let's start at this battery and we will follow these arrows that we set up earlier. So we go the wrong way across the battery. That's going to cause a drop instead of a rise. So following along, we go across a resistor with our arrows, so we go in the same direction. So that'll cause another drop. Keep moving along, we cross another resistor, but this time in the opposite direction. So these black arrows, that's where we said the current was going. They move down, but we're moving up. So this resistor is going to cause a rise instead of a drop. And then on our way from B to C, we don't hit anything, and we're back to where we started. So let's set up this second equation here. I might be able to fit these both on the screen now. Alright, so we know everything has to add up to 0. That's where we start. We cross the battery the wrong way. So we have negative V2. Keep moving along. We cross the resistor the right way. So that's going to be negative, what do we call that current? I1 minus I2. So the current moving through resistor 3 is I1 minus I2. We set that up a while ago. Okay, and then the last thing, we cross resistor 2 the wrong way. So we're going to have to increase our potential here. So plus, and the current in resistor 2 is still I2. do the same thing we did before, plug in some values and try to clean it up. So negative 8 volts minus, alright, R3 is 2, so 2 times I1, and then 2 times negative I2, so we'll have plus 2 I2 plus, our value for R2 is 3, so 3I2. And simplify it a little bit more. 8 equals negative 2I1 plus 5I2. So on Friday, the way that Gail saw it would be super easy to solve this system would be elimination. And yeah, it may be one of the easier ways, but the way the notes are set up, we kind of are forced to do a substitution here. So we actually need to take this equation that we just got and solve it for I1. So it'll look like 8 minus 5I2 divided by negative 2. And that's going to be I1. So we're going to solve this by substitution. So if we plug it into this equation that we had before, we have 4 times, I'm going to pause for a second, alright, so we plugged in for I1, I just divided both things here by the negative 2, that's why this looks a little bit different than we had here. Alright, so do some math stuff, and you will get down to 13I2 is equal to 12. Sorry, 28. So I2 equals 28 over 13 amps. So the current across resistor 2 is 28 over 13 amps. Now that we know that, we can figure out R1 and R3 a lot easier by just plugging in I2 for the other equations that we have here. So if we want to figure out what is the current I1, then we have 5 halves I1 minus 4. Oh, sorry. Oh my gosh. How do you guys learn anything with me making all these mistakes? Alright. 14 over 13 amps. If we plug in the 28 over 13 in here for I2, we'll get that I1 is 14 over 13. And then to get the last current, the current through resistor 3, we said that was just I1 minus I2. So 14 thirteenths minus 28 thirteenths would be negative 14 thirteenths. Alright, so negative current, that sounds kind of strange, doesn't it? Um, what the negative current tells us is that we actually drew our arrow the wrong way. But, I mean, we knew that. We went the wrong way across a battery. We knew something was wrong there. So if you ever get a negative current when you're applying Kirchhoff's laws, that just means um, it goes in the other direction than the way that you actually thought it did. So that's why we said earlier it doesn't matter how you draw your arrows, because if you're applying Kirchhoff's laws the right way, then you'll run into a situation like this where you get a negative and it tells you, hey, you made a mistake, it's actually like this. And it's not like the kind of mistake where you have to go back and do everything all over again. It's just oh, here's the wrong direction.